All right, we previously worked with a case where we were working with a constant speed type of situation. So now let's look at something where we don't have constant speed. So we're going to do a quick motion diagram here for an object that is increasing speed to the right. So if I'm increasing speed, then I know my little dots are getting farther away. So maybe I have something like this. I'm going to go ahead and number these guys. So we'll say this is 0, 1, 2, 3, and 4. It says our positive direction is to the right. So I'll go ahead and label that axis here. And then we do like to put those little arrows in here, right? So here's my little velocity vectors. So in this particular case, we are increasing speed. We're going to the right. So I know I do have an acceleration. And I'll go ahead and just say, so my acceleration, if I'm increasing speed, that means my my velocity and my acceleration have to be in the same direction. So my acceleration is going to be in this positive direction to the right, as we have shown here. And then the other piece I'm going to go ahead and just say that this X position here, we'll say this is 0. So X0 is equal to 0. So we're increasing in our X direction as we move to the right. So similar to what we did previously, we're going to take this motion diagram and I want to plot it on a position time graph. So for my position time graph, we're going to have T on the X axis. And I'm going to try to extend this out a little bit so I have a little bit more space. And then instead of having Y on that vertical axis, remember we're putting our position piece. So on the vertical axis, that is our X representing the position of the object. So we're going to say here our starting point T0. Actually, I'll go ahead and label. So this is T0. We'll say this is 1, 2, and then I got a 3 somewhere out here. So for T0, we're at X equals 0. So I'll make a little point here. Then at T1, so again, similar to what we did previously, I'm going to kind of think about from my motion diagram, how do I transpose that onto this position time graph? So I've got a little change in position. So I'm going to draw that here. I've got just like this little piece here. So my X1, so we'll say this is X1, this is X0, might be this point right here. Then if I go from, I want to get to X2, so time equals 2. Now, since our object was speeding up, we're going to have a greater displacement vector, velocity vector up there in our motion diagram, right? So that's going to manifest the same way on this graph here. So my displacement vector is going to be a little bit bigger. So my X2 point is going to be maybe up here. And then if I can see if I can get one more in here, if we look at from 2 to 3, so again, we're going to have a bigger displacement. Our velocity vector is bigger. So we might have something kind of like this here. Okay, so I'm kind of going away from my graph a little bit or beyond my graph a little bit, but I've got our 4 points. So here's X0, here's X1, X2, and X3. And we can see that because we're increasing speed, so if I connect these and try to connect them kind of cleanly, if I connect these, we can see that I don't have a straight line, right? I don't have a constant slope like we did in the previous example. So in this case, my slope is changing as I go from T0 to T3. So if we know our slope is not constant, and we remember that slope is velocity. So if slope is not constant, that means V not constant, right? And we already know that from this motion diagram, but sometimes we'll be working with a case where we don't have the motion diagram. We're just analyzing the position time graph. So we want to be able to look at that position time graph and recognize immediately that if the slope is not constant, then that means that our velocity is not constant. So if we think about our velocity as presented on this graph, I can still think about like an average velocity, right? So I can do an average velocity from points 1 to 2. So if I wanted to do like V average from 1 to 2, this would be my change in position from 1 to 2. Let me do my delta X here. So delta X from 1 to 2 over my delta T from 1 to 2. And so if I look at that, that's change in position over change in time. That's basically that slope. And I'm looking specifically from points 1 to 2. So that's, and I see I initially drew that as a from 0 to 2. So I did over here, say 1 to 2. So I'm going to change my points here. So if I want to know the average velocity from points 1 to 2, that's just the slope of the line from t equals 1 to t equals 2, right? And so if I look at this line, so this is the average velocity from 1 to 2, right? That average velocity obviously isn't exactly the same as the velocity at all of these points through the interval, right? But that's just going to give me the average from 1 to 2. I could also do the average from like 0 to 3, right? I'm going to see if I can get rid of some of this stuff in here so it's a little less crowded. Let me put that line back in here. So my average from 1 to 2 was kind of this line here. If I want to do average from 1 to 3, I might go from here, right? I'm going to do the same sort of thing. I'm just looking for the slope between those 2 points. So the slopes here are different. So the average velocity from 1 to 2 is different from the average velocity from 1 to 3. So we oftentimes are interested not just in that average velocity, but we're interested in the velocity at a specific point, right? So in our motion diagrams that we have up here, so if I have these, let me get rid of this here. So if I think about this interval, I want to just get rid of that highlight here. If I think about this interval here that I'm highlighting in blue, we can think about the average velocity being the velocity across the interval, right? So that's the average velocity from point 2 to point 3. But I might also want to know, and we will want to know, the velocity at this point, this specific point right here, and the velocity at this specific point right here. And so whenever we think about an interval, we want to think about kind of the endpoints, the starting point and the ending point, and then what's happening across the interval. So the average velocity is happening across the interval. These velocities here are going to be what we're going to call instantaneous velocities. So these are going to happen at very specific points in time. And so if we look at the position time graph, we can get to those instantaneous velocities by basically thinking about that slope between 2 points, right? So this, again, this gray, this is my average velocity from 1 to 2. If I shrink this time interval, right, the smaller I make this time interval, the closer I'm getting to approximating the actual value of the velocity at a given point in time. And so to do this, we use the limit as my delta t is going to approach 0 and ultimately get to our derivative that we use for our instantaneous velocity. So we are going to represent our instantaneous velocity is going to be v sub x. So our average, we use that little AV to specify that that's an average velocity. To distinguish between that, if we have just v with the subscript x, this is just going to mean we're talking about an instantaneous velocity at a given point. So this is going to be the limit as my delta t goes to 0 of my delta x over delta t. So we still have that same direct definition for our average, but we're shrinking that delta t on the bottom. And when we do that, we end up with our, not dv, this is dx dt. So that derivative piece. So our instantaneous velocity, I'm just going to write this here kind of together. So this is a relationship that we are going to be using. So that instantaneous velocity is going to be the derivative with respect to time of our position. And so sort of practically in our graph, what that is going to tell us about is the slope of the tangent line at time t. So at this point, this slope here, so this is that tangent line for t equals 0. This is going to tell me about my velocity at that point. If I'm here at time t equals 2, that tangent line has shifted. The slope is different, right? So this is going to be my vx2, and this is going to be my vx1. So at any point on that curve, we can indicate or think about what the velocity is at that particular point by thinking about the slope of the tangent line at that point. If we want to go then from our position time graph to the velocity time graph. So again, we want to be able to make those connections, position time graph to velocity time and velocity time back to position. So we'll do some practice with both of those. But if I go from position time graph to my velocity time graph, let me go ahead and label my axes here. So we're going to have now Vx. So that's my velocity on the vertical axis. And then we will still have time on our horizontal axis. So remember in our previous example, if the velocity was constant, then we would just have a nice straight horizontal line for our velocity time graph, right? And so this gray line is indicating a positive velocity. Sometimes it's helpful to throw a little 0 in there. So everything up here is positive. Everything down here would be negative velocity. So the above the 0 is just indicating a positive direction. Below the 0 is indicating we're moving, our object is moving in the negative direction. So the gray line I have on there, that's showing if I have something that has a constant velocity. The example that we're working with here does not have constant velocity, right? It has a changing velocity. And so a couple things that we want to note. So in the curve that we have above, and I'm going to just throw one over here. So we have I'll make this blue. So we have a curve that looks kind of like this. So one of the first things I want to recognize is the slope. So remember, for the position time graph, the steepness of the slope is going to tell us how fast, and then whether it's positive or negative is going to tell us if our velocity is positive or negative, right? If that slope is positive, our velocity is positive, the slope is negative, our velocity is negative. So if we look at the example that we have here, the slope is positive through the entire range of motion. So we're not going to do anything with the negative. We're not ever going to cross that 0 and head into the negative section of velocity here. The other thing when we're making the connection between position time and velocity time, I always think it's helpful just to pick a few points, right? And so if this curve doesn't immediately look to you like we're increasing speed, pick 2 points, draw your little tangent lines at that point, and think about what the slope is. So for this first point here, we have a small slope or less steep slope, and here it is steeper, right? And so at the low end of my time, as I'm closer to 0, I'm going slower, and here we're going faster. So that means on my velocity time graph, I need to have something that is going to show me going slower. So over here, I'm down the 0 end, and I need something going faster. So my connection between my position time graph and velocity time graph needs to match up with what's going on with those slopes on the position time graph. So here, slow or low slope, less steep slope means we're going slower. Here, we're going faster. So that tells me through this range of motion, of the example that we're working with, my speed is increasing, right? Because that slope on the position time graph is going to increase. And again, this would connect back to that motion diagram we had at the top, right? So in the motion diagram, we were showing that as I go from T0 to T4, I think I have labeled there, my speed is increasing. So that the distance between those times is greater, meaning that we are going faster at the end than we were at the start.